Right. So lots of little things that we're going to be working on in this video for chemistry, reaction rates, collision theory, potential energy diagrams. Make sure we're hitting all the key points. Okay. So the rate of reaction is how fast or slow the reaction is. So when I talk about these, a lot of times I'm going to use physical change instead of chemical change because it's something that your brain can recognize and help you remember. Just remember, when we're talking about reaction rates, we're talking about chemical changes. So increasing the temperature typically speeds up the reaction rate. If I have iced tea or tea in a cup, hot tea, okay, when I have all those little ice cubes in there, it's making that colder and less sugar dissolves. Okay, we're at a lower solubility. We can get more sugar to dissolve when we're in the hot tea. We can also get that sugar to dissolve faster when there's more temperature. Same thing for a reaction. That reaction can occur faster because it can get to its activation energy sooner. What else? We can use a catalyst. So a catalyst is basically a coach in the reaction. He's not a reactant. He's not a product. That's why the catalysts are listed right above that yields arrow. So they can be any number of things, whatever is needed for that particular reaction. Platinum is one that is often used. So Coach Platinum's on the sidelines going, come on, speed up, speed up, speed up. And he's still going to interact with you, but he's not a reactant and he's not a product. And there you go. You're going to be able to get to your products faster. Increase the surface area. Back to that sugar. If I have a teaspoon of sugar that I put in, teaspoon of sugar, all those little sugar particles are all over the place. Or I put in a sugar cube, same mass, conservation of mass, so our controlled mass, basically, we're doing an experiment with the same mass to compare what's happening when I have more surface area. Wow, those water molecules can get in between all those little particles a lot faster because there's a lot more surfaces to interact. So a powder is going to have more surface area than a cube. The cube, the water is going to take its sweet time going through the top layer and then going through the next layer. So it's a whole process to break it down. So the sugar will dissolve faster when you have more surface area. How about concentration? So if there's only 2 people on a big old field, or there's 1,000 people on there, how many interactions are you going to get? Those 2 people are going to take a long time to get together because you also have to get together at the right speed and the right orientation for a chemical reaction to happen. So those 2 are going to take a lot longer than if I have 1,000 of these guys randomly bumping into you. Eventually, we're going to get somebody with the right speed and at the right angle so you have a chemical reaction. So if I have more concentration, I'm going to speed up getting to my products. Increase pressure. I'm not going to explain this necessarily in a chemical way, but again, it's to help you remember. If I am squeezing something, what's going to happen? All your particles are going to try to get into one spot, which means they're all kind of going into one place. And you are what? Going to have a better chance of them having the right energy and the right orientation. So your reaction goes faster. How about slowing down? It's the opposite of everything. A catalyst and the inhibitor are just opposites. An inhibitor inhibits or stops the reaction, whereas a catalyst speeds up the reaction. If you don't have a catalyst or an inhibitor in there, then you just have the reaction rate that you would find in a lab. So oftentimes you're going to test different catalysts or inhibitors to get the reaction speed that you need for your particular project. All right, now this graph, most of this graph, you can actually know if you're good at graphs without a lot of chemistry knowledge. There's only 2 chemistry points that we need to know. What are reactants? What are products? Reactants are what's on the left of the reaction. Those are our ingredients. And these guys are shown in the solid line. So I'm just going to add a little color here. I know it's a bad drawing by me, but so that you can see what it looks like. The products are over here, what's produced or synthesized. This is a synthesis reaction because we only have one product created, and that is the dashed line. And now, since we have those little colors here, that's going to help us figure out what's going on. What happens when we increase the pressure to the concentration? So here's my pressure down here, increasing the pressure. Which direction is that going to go? To the right. So even though there's not numbers on here, we can assume that zero's on the right. So increasing the pressure is going to the right on the graph. Nitrogen gas. Which one's nitrogen gas? Right here. He's a reactant. So that is this curve. As we go to the right, what is happening with our concentration? It's starting up here high and it's going down there. So it's decreasing. So nitrogen gases concentration is decreasing with added pressure. What about hydrogen gas? He's a reactant. He's following that same trend. Hydrogen gas is a reactant, so he's decreasing concentration with added pressure. Ammonia, he's on the flip side there. And the pressure is increasing. We're still going to the right, but when we go to the right, what's happening? We are going up the graph. So ammonia is getting higher, increasing concentration when we increase the pressure. Does this make sense? What did we just learn about? If we increase the pressure, we increase the rate of reaction. If we increase the pressure, we increase the product. If we increase the pressure, we are going to the right side. We're speeding up the reaction. So that does make sense. All right, let's see. We have copper strips are placed in two separate beakers. Now we're just showing one here, but we can get the idea from this one. Copper strips. One beaker has 5 molar sulfuric acid, another 2.5 sulfuric acid. Okay, so this is some sulfuric acid solution of some varying concentration. Okay, and then what is going to happen? What is different? Okay, so let's look. What is different? Everything else we're going to assume the same. So the amount of water, the mass of the strip, the surface area of the copper strip, the size of the beaker, the temperature, we're going to assume all that other stuff is controlled and the same because we really want to only change one thing on a basic experiment so we can really know. So what did we change? We went from 5 molars to 2.5 molars. What are molars? Concentrations. So we are changing the concentration. And then we want to see what's going to happen. Let's write a hypothesis about what we think will happen. So hit pause and try to put it in this if then because format. And if you need a little help, if IV, then DV because key term. That's a way to remember to make sure you're hitting all the spots. If independent variable, what's the independent variable? The thing that the experimenter changes. Okay, if the experimenter changes the concentrations of acids, the 5 molar sulfuric acid will, let's see what will happen, react faster than the 2.5 molar sulfuric acid because if we increase concentration, we increase reaction rate. So increase concentration, increase reaction rate, that was my key term. My IV is what the experimenter did, changes the concentration. If we change the concentration, then the 2.5 molar sulfuric acid will have a slower reaction rate because concentration is related to reaction rates. Lots of different ways you can say it. You don't have to say it exactly how I say it, but you do want to make sure if then because format, if IV, then DV, because key term. The thing sometimes people forget is they will say this and they'll say, if we use different concentrations, then the reaction will change. That's not specific enough. Is it going to increase? Is it going to decrease? Make sure you're specific in how it's going to change, because that's what I'm going to be recording. My DV is my reaction rate. So I'm going to see how my reaction rate depends on my change in my concentrations. Okay. What's one thing that this hypothesis is incorrect? You really should not have pronouns. We have not gotten to that level yet, but it's coming. Try to avoid those pronoun uses. If the researcher, if the student, if the teacher, if different concentrations of acids are used, you can put it in any type of format, but do try to avoid those pronouns. All right, which reaction is faster? So in this one, we might not actually need a lot of chemistry knowledge either, just a lot of graphing knowledge. Check and make sure they're not messing with you with the scale. Okay, I'm going from 0 to 10 seconds. And on the bottom, 0 to 10 seconds. So you're checking the scale, making sure the divisions are the same, and the units. And the Y is going from 0 to 0.1 on both, and it's moles per liter, or a molar concentration. Okay. So again, it's the same. Always check that first. All right. Now, what's the next thing we can do? We can look at the slopes and see what happens. So we can analyze different parts. So what's happening in this first 1 second? We're going from 0.10 to 0.03. So the first step is going from 0.10 to 0.03. What about on the bottom one? 0.10 after 1 second to 0.04, 0.10 to 0.04. This guy here only lost 0.06. This guy up here lost 0.07. This guy is going slower. Now, you don't want to just look at one part and go, okay, I'm good. Check it a couple of different places. The other place that you can check it, okay, is how long does it take to get to a certain point? So if you look here, you can see it's called an asymptote. We are ending up at 0.01. So something is going on that we're really stopping that reaction at 0.01. And where does that happen on the top graph? At 7 seconds. Okay. Where do we hit that line on the bottom one? Either 9 or maybe even 10. If you notice, it's still moving, but let's go with 9 to be conservative. What is that telling us? This bottom one took 9 seconds to get to the same place the other one took in 7. Who's faster? The person that gets to the end of the race at 7 seconds instead of 9 seconds. So again, you don't necessarily need to know and remember what the concentrations are for this one, but you do have to be able to look at the graph. Just make sure you look at it at multiple spots. There is a couple other ones in year 2. You're going to learn an even more exact one to measure, but for year 1, use your math knowledge. Okay. And here's our potential energy graph. We have our activated complex, and so the top of our activated complex is 200. We have our reactants are at 150, and our products are at 50. Now, there's no units here, so you don't know if it's joules or kilojoules. It's probably kilojoules, but it's still a way to compare what's going on. So our activated complex is at 200. What about my activation energy? We got to know what activation energy is. That's the energy to start a reaction. It does not matter if it's endothermic or exothermic. It still has to get that reaction started. It still has to, what I call it, go over the hump. You got to get over the hump before you can then coast for the rest of the time. So you got to work hard at the beginning, regardless if you're endothermic or exothermic. How much does this guy have to work? Well, he's already at 150. He has to get to 200. So 200 minus 150 is 50. The activation energy needed to start this reaction is 50. The reactant energy, like we said, is 150. The product energy, like we said, is 50. The enthalpy of reaction, or the heat of reaction, is what is the difference between the two. So if you do it in the correct order, products minus reactants, 50 minus 150, you're going to get the correct sign at the end. Negative sign means exothermic. I come back over here to my graph. Can I confirm that? Because sometimes I mess up my signs. The reactants have more energy than products. The products have less energy. Why? They're lower on the graph. They have less energy. Conservation of energy. We can't just magically create or destroy energy. It had to go somewhere. It's not in the reaction anymore because it's not in the products. So we lost energy. How else could we say that? Energy exited. So this is an exothermic graph. So then our negative sign here confirms we did it the correct way around. Right. In this reaction, the enzyme is acting like what? So when we're here, let me use a different color. When we do not have the enzyme, look at my activation energy, my EA, energy of activation, the energy to get the reaction started, is that size. Again, I don't have numbers, but I don't need numbers for comparing. My activation energy when there's an enzyme, what can I say? It's less. Okay. Why does this matter? Well, instead of having to go on the reaction and go, my reaction now goes. What happened? I had a coach. I had a coach that say, you're working too hard. There is a shortcut. Take the shortcut. Okay. There is a cutout so that you can make the same thing go faster. That is what your goal is to do, is to make sure you can go faster. What key term do we use for faster? A catalyst. Now, the official definition of a catalyst is it speeds up the reaction by lowering the activation energy. So it works a little bit differently than some of the other substances. We increase the temperature so we can get to the standard activation energy faster. But a catalyst physically changes our curve setup. So that one works a little bit differently. And that's all for today.